So this is a walkthrough of the AS Unit 1 specimen paper, which CCEA have produced, and it's on their website. I'm going to take you through it and just talk through the way I think about these questions, and hopefully that will help you get an idea of how to approach them yourself. So you see the time for this is 1 hour 30 minutes, and there are 16 questions, and the total mark for the paper is 90. So it's pretty much the same as any AS paper. You get a data leaflet which includes the periodic table, and this is it. So make sure that when you're asked for atomic mass or something, you're just using your periodic table to look it up. You're not expected to know them off the top of your head. And the other stuff in the data leaflet that you might find useful is general information like your conversions between tons and grams, meters and nanometers, the molar volume of a gas, the Avogadro constant. The other things there, gas constant, Planck, specific heat capacity, speed of light. You're not going to need them for this paper. The wave numbers here are all for infrared, and then the NMR stuff is for next year, so you don't need to worry about those this year. Not in this paper anyway. So it starts as always with the multiple choice questions. Each one is worth 1 mark, and it's really important that you make sure you connect the dots as you're shown on the answer sheet. Doesn't matter what you write here beside the questions, it's the answer on the answer sheet that actually counts, so make sure that you're putting it in the right place and joining the dots in the right way. The first question here, in which species is the number of electrons equal to the number of neutrons? So the way I would approach this is just to use the periodic table, look up the mass number and the atomic number of each one, and then work out the number of electrons and the number of neutrons. So for A, for boron, it's 9 and 4. For fluorine, 19 and 9. For sodium, 23 and 11. And then for oxygen, 16 and 8. So we know then that the number of neutrons for beryllium is 5. For fluorine, it's 10. For the sodium, it's 12. And for oxygen, it is 8. Then just looking at the number of electrons. So for beryllium, there's no charge, so it's just 4. So we can rule it out because they're not the same. It says electrons and neutrons have to be equal. So we can rule out beryllium. Fluorine, 19. The atomic number is 9. We've got 1 extra electron, the F minus. So that means 10 electrons. So they are the same. So it looks to me like B is probably the right answer, but we'll check the others just to be sure. So with sodium, Na plus, so it's 11 minus 1 is 10. Those aren't the same then, 10 and 12, so it's not that one. And then oxygen ion, the oxide ion, 2 minus, so that would be 8 and 2 is 10, so again, not correct. So I was right, the answer is B, the fluoride ion. Okay, number 2, which of the following states the name of a suitable indicator together with the correct colour change at the end point for the titration of ethanoic acid and sodium hydroxide? So just looking at this question, I would immediately be saying this is a weak acid and this is a strong alkali. And then looking at the diagram, we see that the sodium hydroxide is in the burette and the acid is in the flask. So we're going from acid to alkali. So because it's a strong alkali, I'm going to say it has to be phenolphthalein. And then we're going from acid to alkali. So with acid, phenolphthalein is colourless and it changes to pink. So the answer here is C, colourless to pink. Number 3, gallium nitride is an ionic compound. The electronic configuration of the nitride ion in gallium nitride is, well, we want to find out what the electronic configuration of the ion is. So gallium is a metal, nitrogen's a non-metal, so nitrogen is going to be the anion here. So its atomic number is 7, as you know, so it has 7 electrons in nitrogen. So the nitrogen ion N3 minus would be 7 plus 3 is 10 electrons. So we're looking for one that has 10 electrons in it. So A here, 1s2, 2s2, that's just 4 electrons, so it's not that. B, 1s2, 2s2, 2p3, so that's 2, 4, 7, can't be it. C, 1s2, 2s2, 2p4, so that's 8, that's not right, so it has to be D. When we add those up, it's 2, 4, and 6 is 10, so the answer is D for that one. Number 4, which of the following is the best oxidizing agent? So an oxidizing agent causes other things to be oxidized, so it is reduced itself, and reduction is gain of electrons. So we can rule out B and D because they're already negatively charged, they're not going to gain electrons, so it has to be either chlorine or iodine. So in terms of what is better at attracting electrons, the chlorine is actually smaller than the iodine, so the answer here is the chlorine. As you go down the group, they become less effective at oxidizing things. So that's just, you should know that from the group 7 stuff that we've done from the halogens. Now, number 5, which of the following atoms obeys the octet rule? So we have 4 compounds here. These are examples you should know. So you should know that the B in BF3, we've got 6 electrons around the central boron there, so that's not going to work. The example you know is BeCl2, so when you've got another 2, so there's your BeCl2, which would be linear, and then you've got 2 extra chlorines, and there's 2 minus charge, so you've got an extra 2 electrons. That does in fact obey the octet rule. So just for completion, I suppose we'll do the other ones. So the phosphorus in PCl5, we've got 5 chlorines around the phosphorus here. So when we draw all of those in, you'll see then that the phosphorus actually ends up with 10 electrons around the middle. And I'm not going to draw out the SF6, but it would have 12. You have the 6 electrons from sulfur and 6 more from the fluorine. So the answer there is B, the beryllium in BeCl4 2 minus. Next, which of the following does not have hydrogen bonding between its molecules? So we're looking for something that, well, if something does have hydrogen bonding, the hydrogen is directly joined to an oxygen, a nitrogen, or a fluorine. So we can see here in B, there's an oxygen joined to a hydrogen. In C, it's a hydrogen joined to a fluorine. And in D, the hydrogens are joined to a nitrogen. The only one which doesn't have that is A, which is CHF3. And if we draw out the structure, you see that the hydrogen is only directly joined to the carbon in that case. Number 7, which of the following is a polar molecule? Now, immediately when I look at this, my eye is drawn to D, which is, I've lost the page. Let us see. Apologies, spoilers here. There we go. So my eye is immediately drawn to this one, the NCl3, because my suspicion is that that looks a bit like ammonia. And ammonia, as you know, has the lone pair and then 3 hydrogens. In this case, it's 3 chlorines. So I'm going to stake my reputation here and say that it's NCl3. Just to check, the BF3, you know that that's trigonal planar, so it's not that. The tetrachloromethane does have dipoles, so does the boron trifluoride, but those dipoles cancel each other out because they're all pointing in opposite directions. And the CS2 is like carbon dioxide, so CS, and again the dipoles there all cancel each other out. But with this one, with the NCl3, there's a resultant dipole going in that direction because the lone pair here is repelling the 3 bonding pairs of electrons. Okay, so the answer is D. Number 8, in the periodic table, the element zinc belongs to, well, this is where you look at your data leaflet if you're not sure where zinc is, but it's one of the transition metals. So just to recall the blocks for you, S, P, D, and then the actinides and lanthanides are F. So it is, it's D. It's in there, in the D block. Okay. Number 9, relative atomic mass is defined as, and you know, see, I love their definitions, so this is one you should have off pat. The first one, the average mass of an atom of an element relative to 1/12 of the mass of a carbon-12 atom. That sounds right to me. I'm going to say that it probably is that one. If we look at B, the average mass of an element, so it doesn't say of an atom of an element, so that one's wrong. C, the mass of an atom of an element, so it doesn't say the average mass, so that one's wrong as well. And then D, the mass of an atom, so again, it doesn't say average mass. And this one even says relative to the mass of a hydrogen atom, so that's complete rubbish. Okay, so the answer there is A. And then number 10, which of the following is not produced when concentrated sulfuric acid reacts with sodium bromide? So it helps here if you can recall the reaction of sodium bromide with sulfuric acid, so I'll just write it for you. So NaBr and H2SO4 gives you, as all of these do, the hydrogen sulfate. Oops, right, the hydrogen in would help. So it's NaHSO4 and HBr. Now HBr is able to reduce the sulfuric acid further, and it gives bromine, we need 2 there, and sulfur dioxide and water. So looking at the list here, which of the following is not produced? So you do get bromine, so it's not A. You get hydrogen, so there's the bromine. You also get hydrogen bromide, so it's not B. You get sulfur dioxide there, so it's not D. The one which is missing is hydrogen sulfide, so the answer there is C. And if you remember those reactions, the only one which is strong enough to go on and reduce the SO2 then to hydrogen sulfide and further on to sulfur is the sodium iodide. So those are the multiple choice questions. You really want to be aiming to take no more than 15 minutes to get those done. And then the next block you're trying to get done in, to leave yourself probably 15 minutes at the end to be able to have a good read over your work and to check that you've everything filled in. So, question 11, what is meant by the term orbital? So you're going to have to say something like it's a region within an atom that can hold up to 2 electrons, and then the important bit is with opposite spin. Only 1 mark for that. Okay, I'm going to make a statement here which is going to sound bad because I'm not doing it myself, but it's very difficult when you're writing on the iPad like this to actually write small enough so that you can read it on the video. But when you're answering in the real exam, make sure that your answers fit within the area that you're given. So for example, this next one, draw the shape of an S orbital. I'm going to make sure that it fits in here. An S orbital, you're just drawing a circle anyway, like a little ball. But if I was to go, oh no, I've got it wrong, and score that out and do a big star like this and do it down here, when that's scanned in, because they're marked electronically, you're not actually going to, the marker isn't going to see that. They only see what is actually in that area. So if you do run out of space, make sure you use a separate page and label it carefully so that it's clear what question it belongs to, and then it will be scanned and flagged when the person comes to mark your paper. Okay, part 3, write the electronic configuration for an atom of copper. So you have your periodic table, you use that, and I'm going to write it out longhand first of all. So it's 1s2, 2s2, 2p6, 3s2, 3p6, then 3d, 10, 4s1. Now you can do it in the shorthand using the noble gas notation, which would be AR for argon, and then 3d, 10, 4s1. But you'd probably be more confident just writing the whole thing out as I have done there. Either would get you the marks. The next bit is about ionisation energies. Successive ionisation energies provide evidence for the existence of different shells in an atom. On the axis below, sketch a graph of the successive ionisation energies of oxygen. So if you're not sure what group oxygen's in, you look it up. It's in group 6, and that tells you that the big jump is going to be between 6 and 7. So what I'm going to do here is just throw in a couple of little dots so that I know I'm going to draw my big jump there between 6 and 7, and then you need to show that the ionisation energy increases as you're going across the graph, and that I'm a little bit too far there at the right, so but that the big jump is between 6 and 7. So 1 mark is for the increase, and then 1 mark is for the jump between 6 and 7. Okay, so that's where the 2 marks are from there. Next one, write an equation including state symbols to represent the second ionisation energy of oxygen. So second ionisation energy is from 1 mole of unimolecular ions in the gaseous state going to 1 mole of molecule, or 1 mole of atoms with a 2+ charge in the gaseous state plus a mole of electrons. So explain why the first ionisation energy of oxygen is less than the first ionisation energy of fluorine. Well, if we think about where they are, oxygen is to the left of fluorine in the same period. So the oxygen has 1 less proton than fluorine, so it has a smaller nuclear charge. So that's the oxygen has a smaller nuclear charge than the fluorine. So you would get 1 mark for saying that. The second mark is for saying that the outer electron for both is in the same shell. And that means that shielding is the same for both. That's your second mark. And then the third mark is for saying then that oxygen has less attraction on that outermost electron. That's your third mark. So because there's more shielding, there's the same amount of shielding, but the fluorine has a bigger nuclear charge, it means that it's able to pull that outer electron more than the oxygen. Okay, and I've written it there from the point of view of oxygen having less protons than the apologies. I'm going to try not to keep doing this all night. Okay. So my point was that you can either write it from the point of view of the oxygen or from the point of view of the fluorine. Right, so ionisation energies provide evidence for the order of elements in the periodic table. The ionisation energies of some groups, 6 elements, are shown in the table below. State and explain the trend in ionisation energies in the group. Well, you can see here the trend is that as you go down the group, the ionisation energies decrease. So that's 1 mark for state. The trend, so it decreases down the group. So I imagine there's 1 mark for that. And then you have 4 marks in total, so 3 more points need to be made here. So as you go down the group, these are the things that are not affected. The first thing is that the outer electron is further from the nucleus. So that means then that that outer electron experiences more shielding. Obviously there are more electron shells in between it and the nucleus, and that means that the outer electron is less strongly attracted to the nucleus, and that's just as you go down the group. So 4 things: it decreases down the group, that's stating, and then 3 points to explain. So the outer electron's further from the nucleus, it experiences more shielding, and it's less strongly attracted to the nucleus. Okay, question 12. Uranium, named after Uranus, is a weakly radioactive metal used to fuel nuclear power plants. It has properties and a structure typical of a metal. Describe the structure of uranium metal was the same as any metal. So they're looking for, then there are layers of positive ions. And then the other thing is then that they're surrounded by a sea of delocalized electrons. You see there are 2 marks for this, so 1 for the positive ions and 1 for the sea of delocalized electrons. That gives you tells you what the 2 common isotopes are and says explain why these are isotopes. So the first thing you would always say when you're talking about isotopes is that they are atoms of the same element. And then you're going to say with different mass numbers. So different numbers of neutrons. And I looked at the mark scheme for this, and the first one is for saying atoms of the same element, and the second then is for making this point, but also for saying that the U235 has 143 neutrons, while the U238 has 146 neutrons. So you're actually showing that you can work out the different numbers of neutrons there. Okay, so then we're told that the relative atomic mass is this. Calculate the percentage abundance of each isotope present in the sample. So you know that relative atomic mass is mass 1 times the abundance of, the first isotope plus the mass of the second one times the abundance of the second one, and then divided by the total abundance. So in this case, we can substitute in the values. So we've got 237.979, and that's equal to 235. And I'm going to call the abundance here of this one X, and then the mass of this one is 238. So if the total abundance, I'm going to make it 100. So it's going to be 238 times 100 minus X for this one. So that kind of, when we simplify out what's in the brackets there, 237.979 then is equal to 235X plus 2000 or 238 or whatever that is, that number, minus 238X over 100. So X works out anyway at 0.7%. So that is U235. So remember, we put X here for the abundance of the first isotope, and then 100 minus 0.7 is 99.3% of the U238. So that's your answer. 3 marks for that. So the marks would be, I suppose, 1 mark for getting that right, and then 1 for each of those for putting the values in. Okay, C. The extraction of uranium from its ore can be represented by the following series of reactions. Write an equation for the conversion of UF4 to U. So looking at this schematic, there it is there. So it's just going to be UF4 plus Mg for magnesium is giving us U, and then I suppose the product is going to have to be Mg, magnesium fluoride, so it have to be MgF2. So balance that up. We need 2 of the magnesium fluoride to use up all the fluorines, and then that means we need a 2 in front of the magnesium. So it's UF4 plus 2Mg gives you U plus 2MgF2. 2 marks for that. I would say 1 mark is for the working out what the reactants in the product and the products are, and the other mark is for balancing. Then write an equation of the conversion of UO2 to UF4. That's this one, and this time it's using the HF. So UO2 plus HF is going to give us, that would be, well, it tells you it goes to, up here you can see it goes to UF4, and then it's going to have to be H2O. So again, 2 marks for this, so 1 mark for getting those species correct, and then we're going to have to balance it, so we need 2 oxygens, so 2 in front of the H2O, and then 4 there, and that balances everything up. Now, oxidation state of uranium, complete the table. So, right, let's do the easy one first. So UF4, H fluorine is -1, so -4 for the fluorine, so that means uranium is +4. In this case, we've got 3 oxygens, so 3 times -2, which is -6. So that means it has to be +6. And then the hardest one to the end, so if you're in any doubt, you can work out nitrate. Each oxygen is -2, and each nitrogen is +3. So we've actually, the overall charge here on the nitrate is -1. So we've got 2 times -1, which is -2, and then we have 2 times -2 for the oxygens, which is -4. So we've got -4 and -2 is -6. So the total there then for the uranium would have to be +6 again. Okay, uranium nitrates, or UO2 NO3 twice thermally decomposes to produce uranium trioxide. What's the systematic name for NO2? Well, each oxygen is -2, so it's -4, so the nitrogen then has to be +4, so that's going to be then nitrogen 4 oxide. And that's just what the systematic name means. It's putting in that Roman numeral for the oxidation state of the nitrogen. How would you show experimentally that oxygen was given off in this decomposition? Well, if you get this question in the real thing, this is an absolute gift. You just need to say relights a glowing splint. Okay. Now, next, number 13. Boron nitride has the chemical formula Bn and exists in two physical forms. These structures A and B are shown below, and they closely resemble the two allotropes of carbon, which is immediately what you would say. You would say that this looks like graphite and this one looks like diamond. So boron nitride is used as a lubricant in pencil leads and also used in cutting tools and drill bits. Suggest why the boron nitride with structure A can be used in pencil leads. Same reason that the graphite can. So it's just really, do you know the answer for graphite? Yes, transfer to this. So we've got layers which can slide over each other. And those layers can slide because they are held only by weak forces. And we know that those weak forces are van der Waals. So 1 mark for saying they're sliding and 1 mark for the van der Waals. Suggest why the structure with B is so hard. So again, this is just exactly the answer you would get for diamond. So it's a 3D giant structure. And there are many strong covalent bonds. Now, because it's boron nitride, we know that it's covalent. So, okay. Suggest why boron nitride with structure B does not conduct electricity. Well, there are no, all the bonds are used up. There are no free electrons. You could say all the electrons are used in bonds, but it's the same thing. Okay. Number 14. Sunglasses can be made from photochromatic glass, which contains small amounts of silver 1 chloride and copper 1 chloride. The first thing I would do here is write down the formula for those, so AgCl and CuCl, because if they're giving them to you in the question, they're probably going to be important. So as sunlight passes through the glass, silver ions are reduced to silver atoms, which cluster together and block the transmittance of light, resulting in the darkening of the glass. The chloride ions are oxidized to chlorine atoms. It's probably going to be important as well. So calculate the maximum mass of silver ions that can be formed from 0.287 grams of silver 1 chloride. So you need an equation for this. So we've got silver chloride, and it's reacting with well, don't need anything else in it really. It's just saying that the silver chloride is giving us silver. It's a 1-to-1 ratio, so we're going to work out the number of moles of the silver chloride first. So the relative formula mass of that, you look up silver in the data sheet, it's 108. Chlorine is 35.5, so that gives us 143.5. And then the silver, just I'm going to write that in, is 108. So your number of moles is mass divided by the formula mass, so that is 0.287 divided by 143.5, and that gives 0.002 moles. So then you have your 1-to-1 ratio here. So we're also going to get 0.002 moles of the silver. So the mass of the silver is 0.002 times 108, which is 0.216 grams. So 1 mark for working out your number of moles of the silver chloride, and 1 then for getting the mass of the silver correct. Write an equation for the reduction of silver ions to silver atoms. So it helps if you remember that it's silver 1 chloride, so that means it's going to be Ag plus, giving you Ag. And to balance it up, we need an electron in there. That's it, job done. So in exposure to light ends, the chlorine atoms are reduced by the copper ions into chloride ions, and the copper 2 ions produced then react with the silver atoms. So write an ionic equation for the reaction of copper 1 ions with chlorine atoms. So that's going to be Cu plus Cl2. It's going to give us, it turns into copper 2 ions. So Cu2 plus and 2Cl minus. And need to balance that up. So need 2. No, we're okay. Yeah, we've got 2 from the chloride minus 2 and plus 2. Yeah. Looking at the mark scheme, it just says Cl and 1 Cl minus. I'm not sure how that could actually be the case. There are a couple of mistakes in the mark scheme for this one. With it being a specimen paper, it hasn't really actually been marked by any teachers. So I'm going to go with that anyway, because it says with, it says chlorine atoms. So that's where I've gone wrong. I'm going to change, I'm going to use my discretion and go back and change that. So it should actually be Cu plus Cl gives you Cu2 plus and Cl minus. So I could say that's just to illustrate the importance of reading the question properly, but it's just me not reading it properly. So copper 1 chloride, similar to that used in photochromatic glass, can be prepared in the laboratory by reacting copper metal with copper 2 oxide and hydrochloric acid. The equation for the reaction is given here. So explain using oxidation numbers why this is disproportionation. So what I can see is on the left hand side we have copper oxide and copper, and on the right hand side we have copper chloride. It's the only thing that occurs on both sides, so that's what I'm looking at here. In copper it's 0, in CuCl then it's going to be plus 1 because the chlorine is minus 1, and then copper oxide is going to be plus 2. So how do I explain this? Okay, so the copper is reduced from plus 2 to plus 1, and it's oxidized from 0 to plus 1. So remember, if it's oxidized, it's getting more positive. If it's reduced, it's getting more negative in terms of the oxidation number. And then to say that disproportionation is where one species is both oxidized and reduced in the same reaction. So in terms of where the marks are coming from there, 1 for talking about the reduction, 1 for the oxidation, and then 1 for what disproportionation actually is. So that's your explaining using the oxidation numbers. So you're illustrating with the oxidation numbers in the first 2 points. suggests why the copper chloride forms as a precipitate. The only reason you should ever have to give for something being a precipitate is it is insoluble. Otherwise it wouldn't precipitate out. Right, D. Copper 2 chloride can be produced in the laboratory by the reaction of copper 2 carbonate with hydrochloric acid. Calculate the volume of hydrochloric acid, 1 molar, needed to react with copper 2 carbonate to produce 2 grams of copper 2 chloride. Give your answer to 2 significant figures. So remember, if they're telling you the significant figures to use that in your answer or you don't get the marks. So, balanced equation for this, CuCO3, the copper carbonate, reacting with HCl, which is the hydrochloric acid. That's going to give us copper chloride and water and CO2. And let's see, balance it. We need 2 moles of hydrochloric acid for every 1 of the calcium carbonate. So we're told that this is 1 molar and we want the volume of that. And we know we have 2 grams of this. The formula mass of copper chloride then 64 for copper, 2 chlorides is 71, so that is 135. So the number of moles of your copper chloride is 2 divided by 135, which is 0.01481. And this is actually one where if you look at the mark scheme in the specimen materials, they've used 63.5 for copper, which is what you would see on some periodic tables, but in the data sheet, in the data leaflet with this paper, it's actually 64. So that's where I'm getting the 135 from, where in the mark scheme it says 134.5. So the HCl to copper chloride here, we have 2 moles of that and 1 mole, so it's 2 to 1 ratio. So for the moles of HCl, it's 2 times 0.01481, which is 0.02962 moles. And then we can use number of moles is the molarity times the volume over 1,000, or we can work out volume as the number of moles times 1,000 divided by the molarity m. So that is 0.02962 times 1,000 divided by 1, which gives us 29.62 cubic centimeters. Now remember, 2 significant figures. So 2 significant figures means 30 cubic centimeters for your answer. And they do have negative marking in this, so it's -1 for an error. So just be aware of that. So if you got the right answer, and sorry, I've done it again, yeah, there we go. So if you got the right answer, but you had given it to the wrong number of significant figures, you would lose a mark for that error. Okay, number 15. An interhalogen compound is a molecule containing 2 or more different halogen atoms. I love to throw these new terms at you, so don't be put off if they do. So it's an interhalogen compound with the formula ClF3. It was first prepared in 1930 by the reaction of chlorine and fluorine. That's not really relevant at all. Write an equation for the preparation of chlorine trifluoride. So it must be Cl2 and F2 because they're both diatomic. And that's going to give us then ClF3. So to balance that, we need 2 chlorines. So put a 2 there, and that means we need 3 in front of the fluorine. Chlorine trifluoride bonds covalently. Explain the meaning of the term covalent bond. Nice if you get a question like this again, it's just pure recall. So it's the, can't spell, electrostatic attraction, and it's covalent bond, so it's between a shared pair of electrons and the nuclei of the bonded atoms. Okay, so 1 for this attraction between the shared pair, remember to say pair, and then the nuclei. Then dot and cross diagram to show the bonding in chlorine trifluoride. So chlorine has 7 of its own, so and it's going to share 1 with each fluorine. So let me draw the 3 fluorines here. I'm going to just do dots for them because it's quicker. So the lone pairs on the fluorine, and then 1, 2, 3. So I need another 2 lone pairs. So that's my dot and cross diagram for that. Okay, it reacts with arsenic pentafluoride, another thing you've never heard of, as shown in the following equation. Draw and name the shapes of AS5, this arsenic pentafluoride, and then the ClF2 plus, and explain the shape of each molecule. So you see here there's space to draw it, to name it, and then down here there's space to explain, and 6 marks, probably 1 mark for each structure or shape, 1 mark for each name of the shape, and then 1 mark for each explanation. So we've seen things with 5 before, so you're going to draw your arsenic in the middle, 1 fluorine up and 1 down, and then 3 arranged around the central atom to get as far away as they can. So I'm drawing my little sort of 3D here, and that then is a little triangle in the middle, so it's called trigonal bipyramid. And ClF2 plus, so we've got chlorine, we've got an F and an F, and you saw before that there are 2 lone pairs, so it's going to be like this, and that is a bent shape. So as for the ASF5, you're going to say there the explanation is the 5 bonding pairs repel equally. Okay, and then the ClF2 plus, we have 2 bonding pairs, and those are here and here. Then you also have 2 lone pairs on the chlorine. So I'm going to say 2 bonding pairs and 2 lone pairs, and then you know that lone pairs repel more than the bonding pairs. It's the same explanation really you would give for water. And that leads me into the next bit, which is to predict the bond angle. So you know the bond angle for water is 104.5 degrees. So that's exactly what it's going to be there. That's what you're going to predict it's going to be. Okay, C, saturated fats contain single covalent bonds. Iodine monochloride is an interhalogen compound used to determine how saturated a fat is. Show the polarity of the iodine-chlorine bond in the diagram and explain why the bond is polar. So looking at the electronegativity, it increases up the group towards fluorine. So the iodine is going to be slightly negative. Sorry, the chlorine slightly negative and the iodine slightly positive. And your explanation then, so it's showing the bond and then explaining, so the chlorine is more electronegative. And the iodine. So explain why iodine monochloride has a higher boiling point than chlorine. Well, it's to do with that polarity. So in chlorine, it just has van der Waals. Between the molecules. But with then the ICL, it has permanent dipole-dipole attractions. Between the molecules. The dipole-dipole interact. So the ICL, I can't even speak. Has stronger intermolecular forces. Than the chlorine, because the dipole-dipole interactions are stronger than just the van der Waals. And finally, more energy is needed to overcome the dipole-dipole forces. As they are stronger than van der Waals. Okay, so 4 marks. 1 for chlorine, just as van der Waals. 2nd for the permanent dipole-dipole attractions in the ICL. 3rd for those are stronger, and 4 then if we're talking about the amount of energy you need to break them. Finally, number 16. So you know when you got to number 16 you're in the final stretch, because it's always the last question. So it says sodium iodide is used to prevent iodine deficiency in the body. Iodized table salt contains 1 part sodium iodide to 100,000 parts sodium chloride. Magnesium carbonate is also present as an anti-caking agent. So describe how you would use chemical tests on a sample to prove that it contains sodium ions, halide ions and carbonate ions. So sodium ions, well, that's a flame test. And remember that the acceptable colour for that is yellow/orange. Okay. Second one, the halide ions. I'm just going to say X minus ions. That's, you're going to add silver nitrate. And you never just say add silver nitrate, you have to say solution. Because the examiners don't like it unless you say solution. And then a precipitate. Forms for the halide. Then the carbonate ions. That's where you add dilute acid. And you get fizzing or effervescence. And that tells you that it's a carbonate. 4 marks, so one for the sodium, one for the halide, one for the carbonate, and the other one is for saying dissolve it in water. Okay, final mark. Okay. B, part 1. Sodium reacts with iodine to form sodium iodide. Melting points of each of these substances are shown in the table below. So the sodium's 98, iodine's 114, sodium iodide 662. Explain why there's a difference in the melting points of sodium iodine and sodium iodide. In your answer, refer to the type of particle involved, the nature and relative strength of the attractive forces holding the particles together. Okay. So we're going to start with sodium. So the type of particle involved and the nature and strength of the attractive forces. So sodium it has, what am I going to say, strong attraction between the positive ions and delocalized electrons. So that's the type of particle. And then the relative strength of the attractive forces. So we need to say what the attractive forces are. And this is metallic bonding. Okay. Next we've got iodine. It is a molecular substance. So it's molecular covalent, and it only has van der Waals between the molecules. And these are weak. Okay, then we're going to go on to the final one is sodium iodide. So it is ionic bonding, which is electrostatic attraction between oppositely charged Na plus and Cl minus ions. Okay, so I think I've described the types of particles. Now I need to say the relative strength. So ionic bonding is stronger than metallic bonding. And van der Waals is the weakest. So I think that covers everything. So let me just look at the marks scheme here. Yeah. So 1 mark for talking about the ions and delocalized electrons, 1 for metallic bonding, 1 for the weak bonding with the van der Waals here, 1 for the ionic bonds and the electrostatic attraction between the oppositely charged ions, and then 1, yes, for given the order of the strength. Right, state the colour of solid iodine and that of solid sodium iodide. So iodine, the acceptable colour is grey-black, and sodium iodide is white. Sodium iodide is produced in a reaction between iodine and sodium hydroxide. Write an equation for this reaction. So iodine's diatomic I2, sodium hydroxide NaOH. That's going to give us the sodium NaIO3, sodium iodide NaI, and water. Oh, I'm giving it away. I've balanced it on a page before I did this. So it has to be, when you balance it, it's 3I2, 6 NaOH, and 5 of the NaI. Right, we're nearly there. Sodium iodide solution was made in the lab by dissolving 46 grams of sodium iodide in 25 grams of water at 20 degrees. Calculate the molarity of this sodium iodide solution. Give your answer to 3 significant figures. So if we have 46 grams in 25 grams of water, then 25 grams goes into 1,000 grams, which is 1 litre or 1 kilogram of water, so 1 litre. So 46, then I'm going to multiply that by 40 to give me the mass that needs to go into 1 dm cubed, because it says molarity and that's per dm cubed. So 46 times 40 is 1,840 grams. 2 marks. Assume 1 for each bit there. And then chlorine was bubbled through the sodium iodide solution. State the colour change observed in the solution. So sodium iodide solution is colourless. And when you bubble chlorine through it, the iodine goes into solution, so it goes yellow/brown. And I believe, yep, this is the end of the question paper. So hopefully you stuck with that to the end. I will do the specimen paper for Unit 2 before the Unit 2 exam, so I hope you find this useful.